Alright, welcome back. So this is a continuation for our chapter Fundamentals of Light, where we already discussed the section of illumination. Now it's time to discuss the second section, which is the wave nature of light. And here we go. So have you ever wondered why we can hear things from around the corner, but we can't see? As this guy here, he can hear the radio around the corner, but of course cannot see it. This is because of the property of the light that cannot bend around the corners. Okay, we'll discuss this in details, but till now you have to know that sound could be reflected through walls, and this guy could hear the sound of the radio, however cannot see it, and we'll see how lights behave in such situation. So here we continue. All right, so okay, so what do we mean by diffraction first? So we already discussed in the previous section two behavior for the light, which is first of all, which is the reflection. That's the first behavior of the light. Second behavior, which is the refraction, where the light bend or change its direction. And the third, let's move it to here, and the last behavior for the light when interacting with an object, which is the topic of our study today, which is the diffraction of light. So imagine the light, laser of the light, or the ray of the light coming to this point, which is, we can call it as the edge or a slit. Okay, it's very small opening, as you see here, the slit. So what will happen, how the light will behave? It's going in all directions, as you see. Okay, and that's what we mean by diffraction. Diffraction of the light again. So when the light comes and hit a very small edge or slit, and then goes in all directions. As we see here in this animation as well, the wave of light coming to the slit, the moment it hit the slit, it's diverge. It goes as the wave fronts, not in a single direction, but in all directions. Okay, and that's what we mean by diffraction. So let's see it together. So we call it the bending of the light as it passes through the edge. Edge again is this very small opening, as you see here. Okay, then that's what we mean by diffraction, because the light again goes in every and all directions. All right, next, here, first guy who trying to describe that, called Higgins. He's a German scientist. Okay, he developed what do you call now as the Higgins models. So what he's trying to explain is this one. So again, going to the example of the slit, as you see here in this animation, imagine these lines as the waves. The moment they hit the slit, these waves will turn as a source of light themselves. Let's make the animation again. Okay, as you see here, so every point in the graph, it acts as a new source of light, and that's why we can notice different waves at the same time. They interact together and they go in all directions. Okay, so all the points of the wavefront, remember this is the wavefront here, as you see here, the wavefronts, okay, can be through as a new source, or can act as a new source of small waves. Okay, so that's what we mean by this. Again, so let's see it here again. So the waves come to the slit, as you see here, and it spread and act as a new source, a new point of waves, and they interfere, of course, as you see here, the interference, and goes in all directions. So that's what we mean by Higgins principle, where these small points act as a new source of wave or of light themselves. We continue. Second, or another scientist other than Higgins, which is of course Newton, who also not only described mechanics, also is trying to explain few lights phenomena. So what he's trying to explain also the diffraction. So Newton called the order arrangement of colors spectrum. So what's Newton's trying to explain here? He bring a prism, a glass prism, make the white light as you see here, making the white light, and as an outcome of the prism, this light, the main light, which is the white one, now it's divided into multiple kinds of light, and this is what we mean by the colors. Okay, we are going from the red till violet. So this is spreading is the outcome of Newton's experiment or prism experiment. Again, he's trying to with a white light to diverge or to divide light into multiple colors. So he thought at the beginning that this spreading of light is caused by the prism itself, because there is a problem in the prism itself. That was his first thought. So to repeat the experiment, this time he bring another prism. As you see here, we have two prisms. So we have the white light starting from here. It's diffracted or it's spread into multiple colors, as you see here, and then those colors will converge again to form the white light. So the problem is not the problem of diffraction or diverging of colors is not from the prism itself. Okay, it's coming from the light behaving into such situation. So at the beginning, the light interact with the prism, the glass prism, and then it will diverge or divide it into multiple colors from red till violet, and then the second prism will act in the opposite way, where all the colors will converge and reach the screen here as white color. So the second prism reverses the spreading of the colors at the beginning. Remember, at the beginning we have a diversion of colors or spreading of colors, but however the second prism will recombine them to form the white light. Okay, so that's the function of the second prism. Okay, so different colors of course means different wavelengths. As you see here, that's the result of the light coming out from the prism. So it's starting as white light hitting the prism, and then the light is divided into the rainbow colors, all the colors, from red till violet. What do we mean by colors? Again, in physics, we mean by colors as wavelengths. If we have different wavelengths, means we have different colors. So the red starting from 700 nanometer, as you see here, from 700, it's the biggest here in this spectrum, okay, which is the red color. Less than that, we have the yellow, the green, and then to reach the blue or the violet at the end, which is only 400 nanometer. That's, remember, we are just discussing here or talking about the lengths or the wavelengths. All right, so the longest visible wavelengths as seen as red, as you see here, it's 700, and the shortest is the violet with 700 nanometer. Colors by adding of light. So here discussing the second section. Imagine we have three rays of colors. The first one, which is the red, we have the red color, we have the blue and the green, which are called the principal colors, the primary light colors, red, blue and green. So what if we combine the red and the green together? We get the yellow, of course. The blue and the red, we are getting the magenta color. The blue and the green, we are getting the cyan color, and all of them together combined, we are getting the white color in the middle. Okay, so let's go together with this text. So red, green and blue light are projected into white screen. So that's the beginning of the experiment, and white color is formed in the middle. The white color is formed in the middle. Okay, so again we have the red, blue and green are considered as primary colors. However, we have secondary color, which are the magenta, we have the yellow, also considered as a secondary color, and the cyan as well is a secondary color. Okay, so this text is trying to tell us this information. All right. We continue with the complementary colors. Well, why do we call it as complementary colors? Because these two colors of light, if combined, we got the white color. So imagine we are mixing the blue with this one is called, let's say, the orange. Okay, so remember this is light color. Okay, so what we are getting the white color. Okay, so any two complementary, let's say here the red, this is red and facing the green, let's say. Okay, so also they are called complementary colors. So this one and the green. Okay, so these two are considered as complementary. Any two facing colors here in this diagram are called complementary color. So let's say the yellow and the violet here also are complementary colors. Okay, because if mixed together or when mixed together, we are getting the white light. And that's what we mean by complementary color. We continue. Okay, now we finished discussing the addition of light. Now we're talking about the second part, which is the subtraction of light. Okay, here let's take this example first. All the lights coming to an object, let's say a t-shirt, okay, or to a dress. All lights are coming to a dress or to an object. However, we see here in this example a red shirt. Why do we see a red shirt? Because all the lights coming to this object or to this t-shirt, this t-shirt absorb all these colors and reflect only the red color. That's why we see it as red, because it absorbs all colors except the red color. Why do we see this shirt as blue? This short as blue? Because as well absorb all wavelengths, absorb all colors, but reflect only one. So this is what we call as subtraction of light. It's absorption of light. Okay. So the color of an object depends. Let's read together. Okay, so the color of an object depends on the wavelengths present in the light that illuminates the object. So at the beginning, all colors illuminate the object, all the colors from red to violet. Okay, and also on which the wavelengths are absorbed by that object. So this t-shirt, for example, absorbs all wavelengths. However, it reflects only one, which is the red color. That's why again we see it as a red object, and which the wavelengths are reflected. So again, the subtraction of light is directly related to the color or the wavelengths reflected. So imagine another example when we have green apple. Why we see it as green? Because the green apple attracts all colors but reflect the green wavelengths. That's why we see it as green. All right, we continue. The second part is talking about dyes. Dyes used also to color clothes or objects. So as a summary, a dye is a molecule that absorbs certain wavelengths. Again, absorb, subtract. Okay, remember the title of the paragraph, subtraction of light. Here, absorption as well. Absorption means also subtraction of the wavelengths. Okay, and transmit and reflect others. Okay, so at this example, we take the blueberry, also is considered as a dye used to put colors or add colors to clothes. Okay, the blackberry, it's giving the red color or the violet color, or sometimes it's about red or violet color. All right, so it's considered as a dye, okay, used to put colors to clothes. Okay, they are usually made from what? From plants or insect extracts. Okay, they are usually made from plants. All right, we have multiple examples in nature where the fruit or a vegetable used to dye or to put color to clothes. Pigments now. Pigments is different than the dye because it's about crushed materials. Okay, so the difference between a dye and pigment is that pigment usually made of crushed minerals, Okay, so as you see here in the picture, it's like powder. Okay, also used to put colors or add colors to some clothes or objects, okay, rather than plants or insects. Okay, it's about crushed minerals. That's why we see it as powder. Okay, so pigments, again, it's important to discuss here the pigment. Let's magnify this one. So interesting to discuss here the pigments or primary pigments. We have as primary colors, we have also primary pigments. So what did you notice here? Okay, we have the primary pigments, which is the magenta, the yellow, and the cyan. So let's write it here. Primary colors, if you remember, primary colors, if you remember, they are the red, they are the green, and blue. Okay, they are primary colors. What about the primary pigments? Primary pigments. Okay, they are the magenta, the yellow, and the cyan at the end. Okay, so these are the primary colors, the difference between primary colors and primary pigments. Okay, as you notice, if you can go back to the slide of yes, this slide. If you notice, the red, the green, and the blue are the primary colors. However, the secondary color are the magenta, the yellow, and the cyan. The magenta, yellow, and cyan. So the secondary color, okay, are the magenta, the yellow, and the cyan at the same time. So these three colors are also considered as secondary, not pigment, secondary colors. Okay, however, the blue, the blue, the green, and the red, they are considered as, let's go back to this slide. Yes, this one, the red, as you see here, look at the picture, the red, the green, and the blue, red, green, and the blue, they are considered as secondary. As you see here in the picture, they are secondary what? Secondary pigments. Okay, so these three colors are also considered as secondary pigments. All right, so let's continue. I hope you understand now the difference between the primary colors and the primary pigments and the secondary one. Let's continue with this slide. Okay, so yeah, this slide also discussing what I just mentioned. So a pigment that absorb two primary colors and reflect one color is called secondary pigment. As you see here, the secondary pigment, we have the red as the example of secondary pigment. Okay, absorb two primary colors. What are the two primary colors? Which are the blue and the green, and reflect one. And reflects one color is called a secondary pigment. Okay, this is why we call red as secondary pigment, or even this is applied also for the green and for the blue. So let's note that the primary pigment colors are the secondary color light. So the primary colors, let's say here, the primary pigments are the secondary colors. So that's what I am saying here. The primary pigments, okay, primary pigments here, okay, are the secondary color at the same time. In this way, the secondary pigment as well, the secondary pigment here, the secondary pigment are light primary color. So let's add here, it's light primary color. Okay, are considered as also secondary pigments. We continue. This is the second part of the chapter talking about the polarization of the light. Let's clean the board this time. So now with the polarization of light. So normally the light coming from the sun or natural light is not polarized. It means it's going in all directions. It's not polarized. The moment it passes through a lens, or as you see here in a glasses, and usually we say polarized glass, and they are more expensive usually than normally glasses when they are polarized. So why they are more expensive? Because they don't allow all the light pass through the glasses. So they are more comfortable for the eye. Okay, so let's take this example, this beam of light, or let's imagine a light coming from the sun, which is not polarized, means it's going in all directions. The moment it passes through the lens or this polarization, okay, the light, okay, the moment it passes through, the light is polarized according only to one axis, which is parallel, if you notice here, parallel to the axis of this lens. So we'll be discussing this in a few slides. So by definition, polarization is the production of light with a specific pattern of oscillation. It means that when the light is polarized, it oscillates only in one direction, as we see here, up and down. At the beginning, it was up and down, right and left, in the blue, right and left. The moment it passes through the lens, okay, it's called a polarized light, and it's only into one direction, up and down. Okay, we continue. Okay, here is another example of polarization by filtering. As you see here in this animation, the polarization are vertical. So this light coming, this is a simple model. When it only allows the vertical light to pass through. The one which is horizontal is not allowed to pass, only the vertical one. And that's simply what do we mean by polarization. It's the light parallel to the axis of the lens, it passes through. The one which is perpendicular will not pass. That was for this one. Okay, now let's look at this example here, another example similar to the previous one. So here we have the light, the lamp. Of course, the light is not polarized. As you see here, it's going in all directions. In all directions, okay? The moment it passes through the blue lens, which is the polarizer, it's called the polarizer, and if you notice, it's about the lines are vertical. So only the polarized light, as you see here, the polarized light only will go parallel to the axis of the polarizer. Okay, the light which is horizontal or oblique will not pass through. It's not allowed to pass through, and that's why we use sometimes polarized glass, and they are more expensive than usual, as I told you, because it let pass less light into our eyes, and it's more comfortable for our eyes. Okay, so let's see what this text is telling us. Only the components of the waves in the same direction of the polarizing axis can pass through. Okay, that's in summary. Only the light which is parallel to the axis will pass through the polarizer. Otherwise, the light will be blocked. That's simply what's the function of the polarizer. Okay, this is another example. Polarizing by reflection. So polarizing sunglasses, as discussed, reduce the glare. Okay, as you see here, the difference between the polarized and non-polarized, which is more comfortable to the eye. Of course, this one, the polarized, okay, this scene is more comfortable to our eye. However, this one, the non-polarized, maybe will make a headache, because the eye is attracting more information. More light means more information. So how to reduce that? We make a polarized sunglasses to reduce the glare, okay, from the polarized light reflected off roads. Okay, so this polarized lenses also used in photography domain. For photographers, they also used the specific lenses to get such image, okay, or filters over camera lenses to block the reflected light. All right, let's continue. Yes, so here we go. Now talking about the second part of the polarizing part, which is the Malus law. What if, so Malus is a scientist who discussed or put a condition, what if we put two polarizers at the same time? As you see here, we have, this is the first polarizer and that's the second polarizer. I don't know if it's clear. The first one have a vertical axis, the second one has what? A horizontal axis. So what can you imagine? What do you imagine from here, from this law, Malus law? Okay, let's start from the beginning. Let's start from here. So the source of light, it's of course unpolarized light. It's unpolarized means the light coming in, let's say in all directions. Okay. The light is not polarized. It means it's going in all directions. The moment it passes through the first polarizer, of course, the other directions will be blocked, and only the light, which is parallel to the x of the polarizer, will pass through. Okay, that's okay till now. So let's consider this light here have an intensity of I0. The intensity of the light here, let's call it I0. The light, after passing through the first lenses, let's call them I1, having intensity of I1. So this light will continue passing through to hit another polarizer, but this time the x is perpendicular to the first one. So if this one is vertical, this one is horizontal. So what can you imagine? Look here, no light is passing through. We have no lights. I is equal to 0. So here the I2 passing by the second polarizer will be equal to 0. It's equal to 0 because no light. No light is passing. Why? Because this light that passed through the first lenses, which is vertical, let's call it here, it's vertical, having vertical direction. However, this one is horizontal. This one having horizontal axis. So they are perpendicular to each other. So of course, no light will pass through. Let's say here, no light is passing by. Okay, that's why the intensity is equal to 0. We have no light at the end. Okay, and that's what do we consider as Malus law. If the two axes, okay, if the two axes having 90-degree different in directions, so no light will pass. Okay, every time they are perpendicular to each other, no light will pass. Okay, so suppose you produce polarized light with a polarizing filter. What would happen if you place a second polarizing filter in the path of the polarized light? So this question asked by Malus. What if we put or we add a second lens or a second polarizer? What will happen? Okay, if the axis of the second is parallel to the first, the light will pass. Imagine these two polarizer, both of them are vertical, so of course the light will pass. But what if the light will pass through? So what if they are perpendicular? What if both axes are perpendicular? So what will happen to the light? Okay, so no light will pass through. So that's the conclusion. So no light will pass through. Okay, if they are perpendicular. If they are parallel to each other, so light will pass. If they are perpendicular, of course the light is not allowed to go through the lens. We continue. Okay, let's clean it first. So this is a continuation of the previous slide. So what if they are put here in numbers or in words? So what if they are perpendicular, means 90 degrees? So all the light is blocked. Okay, so I2, as it's written in the previous slide before erasing the board, I2 will be equal to 0. Why? Because the two axes of the polarizers are perpendicular to each axis, okay, to each other. So of course the light is blocked and I2 will be equal to 0. Okay, type. What if the two axes are not perpendicular? What will happen in this case? We have angles. So let's start the scenario from the beginning here. We have non-polarized light. going in all directions. It passes through the first polarizer, let's call it I1. So here the light is polarized because the X is vertical. So of course here the light, so here is I0. Yes, I0. Here is I1, the intensity of the light, I mean, I1. Okay, after passing through the first polarizer. And here we have a second polarizer. Okay, but look at it. There is some light going by or going through the lens. So having an intensity of I2. But this time I2 is not equal to 0 because there is some light coming out from it. So let's see. Let's discuss this situation. So beginning here we have, it's not polarized. Here it's polarized after passing by the first lens. And here again it's polarized for the second time. So how to write or how to combine this in one situation? So I2, which has a relationship with I1. Okay, I2 is related to I1, okay, the previous one, multiplied by cosine square of an angle. What is this angle here? The angle is the difference between, remember, this angle here, theta, is not any angle. It's the angle difference between the first axis and the second axis. So if you notice here, this one is like an oblique axis. However, this one is a straight one, if you notice. So the angle between these two, you notice, the angle between these two is the angle that we are talking about. Okay, that's the angle that we are talking about. And that's the Malus law, okay, or Malus equation. So again, I2, which is the intensity of the light at the end, is equal to I1, the light polarized by the first polarizer, multiplied by cosine, the angle between the two polarizers. So the angle between, here theta, let's add this, theta, which is the angle between the two polarizers axis. Okay, so this is the angle theta. Okay, it's very important to define this angle before doing any further calculation. So let's discuss this slide here together. So same situation, you place okay, let's clean the board first. So here in this challenge or in this question, you placed an analyzer filter between the two cross-polarized. Okay, they are cross-polarized, mean they are perpendicular to each other. Okay, filters such that the polarizing axis is not parallel to either of the two filters. It's in between. So this is the analyzer in between. And the first and the third one, they are perpendicular to each other, as shown in this figure to the right. Yes. So you observe that some light passes through filter 2. There is some light coming out. Okay. Though that no light passed through filter 2 before you insert the analyzer. Why does this happen? So let's go with the scenario again. At the beginning we have only two polarizer. One, here's the beginning, then we have one, and there is the second one here. Okay, so imagine this one in the middle doesn't exist at the beginning. Imagine this one does not exist. So what can you say? What can you imagine? Okay, what can we say here? Because the first polarizer is perpendicular to the second one here, they are perpendicular. Look at this. The axis here is vertical, the axis here is horizontal. And what we just discussed in the previous slide, when they are perpendicular, so no light will pass it through. At the beginning, there is no light is passing through. Okay, no light. Okay, no light will pass through. But what we did in this question, or what's the question here? We insert an additional analyzer. We insert a third polarizer here in the middle. Here in the middle, we insert a second or a third polarizer, which is coming in between. If you notice, the angle is between the vertical and the horizontal. It's oblique. Okay, so in this case, after the light is polarized by the first lens, it passes through the second. It only allow the light which having this angle to pass through, okay, which having the oblique angle to pass through, and then because they are not perpendicular, remember the second here, the one in the middle, and the second polarizer here, they are not perpendicular. They are not perpendicular because making an angle. Look at the angle here. Can you see? We have an angle here. Can you see it? This angle. So because they are not perpendicular, so there is some light will pass through. Some light will pass through in this case. Some light will pass. Why? Because in this case, when we insert the analyzer here in the middle, they are not perpendicular anymore. Okay, so the analyzer filter is placed at an angle between of an angle theta relative to the polarizing axis of filter 1. Okay, so we insert polarizer in between 1 and 2. So derive an equation for the intensity of the light coming out of filter 2. So we have to derive an equation describing the intensity of the light coming by this filter. Component of the intensity of the light coming out of filter 1. So let's write the equation of Malus. Remember, we have multiple lenses here or multiple polarizers, so we have to write the equation. So the intensity of the light coming out of the second polarizer is equal to the I1 multiplied by cosine the angle squared. Okay, but what's the angle here? Remember, what's the angle here? I'm interested in this angle, which is this one. So what is this angle in geometry? Okay, remember, I'm interested in this one only. So all of this is 90 degree. If you notice here, this ax and the ax here, both of them are 90 degree. Okay, I'm taking from them this angle, which is, as you see here, this part. I'm reducing this part because I'm interested only in this part, in this angle. Okay, I'm not interested in this one here, the above. This one I'm not interested in. I'm only interested in this part. So what can we say about this angle, which is 90 degree, which is in this case it's 90 degree, okay, minus this part, minus theta. Okay, minus this part, this is theta. Okay, minus this angle. Okay, because I'm only interested in this angle here. Okay, so it's 90 degree minus theta, and that will be the equation because we don't have numbers, so that's how we derive the equation out of this figure. We continue with the speed, wavelengths, and frequency of light, which is the most important equation in the chapter of fundamental of light, which is the wavelengths. In this case, the wavelengths is equal to the speed of light, which is c, speed of light divided by the frequency, f. So c, which is speed of light, okay, and f is the frequency of the light itself. The unit is in hertz, of course, speed of light meter per second, and here the unit of the wavelengths is in meter, of course. All right, we continue. Doppler effect. This part or Doppler effect is already discussed when we in the previous years, if you remember, when talking about the speed of the sound, Doppler effect, and that was the equation of Doppler. If you remember, f prime, which is the frequency of the observer, okay, frequency of the observer, f prime is equal to the v in red, which is velocity of the sound plus velocity of the observer divided by velocity of the sound minus velocity of the source where the sound is coming from. Okay, all of this is multiplied by the frequency of the sound. So now let's convert this, not talking about the sound anymore, but talking about the light. So instead of sound, now let's beginning talking about Doppler effect for the light. So let's convert this equation here. So instead of f prime or f observer, yes, we will keep it. So f observer is equal. The velocity of sound is not velocity of the sound now, it's the speed of light, and speed of light, which is c, okay, plus velocity of the observer divided by, again, velocity, okay, velocity of the sound. It was velocity of the sound, now it's the velocity of the light, okay, minus the velocity of the source. We'll consider velocity of the source, which is negligible. It means like 0, okay, comparing to the speed of light. Okay, all of this is multiplied by the frequency of the light, okay, frequency of the light. So remember, here I didn't add any factor because we consider the velocity of the source is negligible to the speed of light. Remember in the previous section, the speed of light, which is a huge number. Okay, so any small number will not affect this huge number. Remember, because c is equal, if you remember, it's equal to 3 by 10 to the power of 8 meters per second. It's a very huge number. Yes. Okay, so any value adding to this one will not affect the equation. Okay, so I will keep it till here. So let's go further with this equation. We can say that c divided by c, which is equal to 1. Here the plus, we'll see it will be plus or minus, because this depends whether we are going away to the source, going forward to the source of light or going away from it. Okay, so that's why we add plus or minus. And v0 divided by v0, which is the velocity of the observer, divided by the speed of light, all of this multiplied by the frequency. Okay, so that's what we mean by Doppler effect when talking about light. Okay, we continue. So let's look at this equation here. It's similar to this one. So f of the observer, this is Doppler effect in case of light. So f of the observer is equal to the frequency, which is the frequency of the light, okay, initially frequency of the light, multiplied by a factor of 1, plus or minus. Again, it depends whether I'm going forward to the source of light or I'm going away from it. So that's what we mean by plus or minus. Okay, velocity, okay, of the observer, okay, divided by the speed of light. So this is the only difference between the Doppler effect regarding the sound and the Doppler effect when talking about the light. There is something interesting here, but before that, something interesting about Doppler effect, which is the red shift and the blue shift. Okay, physicists usually don't prefer to work with frequencies, they prefer to convert it to wavelengths. Okay, they prefer to work with wavelengths, and they deduce from Doppler effect of light, they deduce this equation, which is the delta wavelengths. Okay, the difference between the wavelengths is equal plus or minus velocity of the source divided by the speed of light, and then multiplied by wavelengths. Okay, so this equation is derivation from the previous one about Doppler effect. But something interesting to discuss here. So imagine Doppler effect again, but this time instead of sound, the light. This is the source of light here in the middle. If the light is coming towards me, okay, look at the waves. Okay, of course the speed of the motion will have to be super high to see this such or to notice such difference. So again, if the source of light coming very fast towards me, I see what do we call as blue shift. We have something what do we call as blue shift. In the contrast, if the light is going away from me, so look at this person here, the light is going away from him. So this person will experience something called the red shift. Okay, again I repeat. So we have the blue shift if coming towards, okay, they are coming towards each other. Okay, they are coming towards each other. We have red shift if they are going away from each other. Okay, we have some, that's what we mean by blue and red shift. So let's read it together here. So we say the light is red shifted, okay, when the wavelength is longer than the original wavelengths. As you see here, the red shift, you remember, notice the wavelengths are larger than the blue one. So when the length or the wavelength is longer than the usual wavelength, so that's what we call by red shift. However, if we call it blue shift, okay, if the direction towards the observer, in this case the observer wavelength is shown shorter, okay, as you see here, when the wavelengths are shorter, and that's what we call by blue shift. So again, blue shift if they are coming closer to each other, and red shift if they are separated. Okay, every time they are going away from each other, we are talking about what we call as red shift. And we can see this one, I found this animation as well. If you notice the spectrum, here we have a spectrum, as you see here, from blue to red. When the two planets, here let's imagine the Earth and the Sun, okay, when they are when they start to go away from each other, the spectrum turns to red, if you notice. However, when they start to come closer to each other, the spectrum will turn to blue, start to gain the spectrum. Okay, every time they go away from each other, the red light will dominate the spectrum. If they are coming closer, the blue light will dominate the spectrum. This is in summary, that's what we mean by red and blue shift. Okay, let's start discussing some questions here. Talking about oxygen can be made to produce light with wavelengths of 513 Newton meter. So let's write the given. Here the given is 513 Newton meter. Okay, the question is what's the frequency of the light? So asking for F, frequency. So if you remember the equation where wavelengths is equal to what? Regarding the equation that we just described, where the wavelengths is equal C over F, if you remember. But here I'm interested in the frequency. So F will be equal to C over the wavelengths, okay, which is equal to 3 by 10 power of 8 divided by wavelengths, which is 513 multiplied by 10 nanometer, remember. So we have to convert the units. So this means by 10 power of minus 9. And the answer is, so the frequency in this case will be equal to 5.84, 3 significant figures, multiplied by 10 to the power of 14 hertz. Okay, so that's for question 16 here. All right. So that's the equation, the main equation that we are applying. So the second question, a hydrogen atom in galaxy moving with a speed of, so this is question 17 here. So the speed in this case, or the velocity of this hydrogen atom is 6.55 by 10 power of 6 meter per second. Okay. Remember, going away from Earth. Okay, so going away, so this means we are talking about redshift. Okay, so a hydrogen atom in a galaxy moving with the speed of this number moving away from Earth emit light with a frequency also is given, which is 6.16 by 10 power of 14 hertz. Okay, what frequency of light from that hydrogen atom would be observed? So talking about F of the observer, Okay, so we have two frequencies here. So we are talking about Doppler effect of light. So what frequency of light from that hydrogen atom would be observed by an astronomer on Earth? So we are interested with this one, f of the observer. So what equation to use in this case? So here we have to apply the Doppler effect equation. So f of the observer means the frequency. It's equal, if you remember the equation, f multiplied by 1 minus velocity, okay, of the motion divided by speed of light. Why I put minus? Because remember, it's going away. The galaxy is going away from the Earth. It's separated. It's redshift. So I put minus. If it's blue shift and they are coming closer, we have to put plus. Okay, so f factor 1 minus velocity divided by c. The frequency is given, which is 6.16 by 10 power 14 hertz, multiplied by 1 minus the velocity is given 6.55 by 10 power of 6, okay, divided by 3 by 10 power of 8, okay, and the answer would be equal to 6.03 by 10 power of 14 hertz. What did you notice about the difference in frequencies? It was 6.16. Now the frequency is less. Okay, it's the frequency is less. It's 6.03. Okay, so that's another proof why it's going away, because it's a redshift. We continue with different question. All right, so we have an astronomer is looking at a spectrum of a galaxy and find that an oxygen spectral line of 525 nanometer, while the laboratory value is measured as 513 nanometer. Okay, so this astronomer is seeing the same oxygen spectrum with different values. So in laboratory, first when it was moving, so lambda of motion is equal to 525 Newton meter. However, lambda when it's at rest in the laboratory, okay, normally this is the normal value, which is 513 nanometer only, nm. Okay, so there is difference between wavelengths. So this reminded us about the Doppler effect. We have for the same spectrum we have two different wavelengths. Okay, so calculate how fast. So calculate how fast means we're talking about the velocity of the motion the galaxy would be moving relative to Earth. Explain whether the galaxy is moving away from the Earth or moving towards the Earth. And how do we know? Okay, look at this. From these two values, what can we notice? In the laboratory, normally it's 513 nanometer. When it's moving, it's 525. So the wavelength is getting bigger and bigger. So it's what, if you remember, it's redshift. Okay, it's redshift because the wavelength is getting a bigger value. Normally it's 513. Now it's 525. So the wavelength is getting bigger. So we're talking about a redshift. So we are moving away. So first of all, let's calculate the velocity. So using what equation? So remember, I'm applying, we have wavelengths and asking for the velocity. So we have to apply this equation. So let's write it down. So lambda of the observer, okay, minus the normal wavelengths. Here I'll call the observer, which is of the motion. Okay, and the second one is the laboratory. Okay, equal velocity over the speed of light. Here I consider it as plus, multiplied by wavelengths, the normal wavelengths, which is of the laboratory. Okay, the normal one. Okay, you can keep it without any index here. Index. So what I'm interested in is the velocity. Okay, so I arranged the equation. So now the equation could be written as this one. So it's C multiplied by this factor lambda of the observer minus lambda of the lab divided by this value lambda of laboratory. Okay, so of course when you apply these values, so C of course it's 3 by 10 power of 8, lambda of the observer or of the motion here, or the observer, okay, it's 525 by 10 power minus 9 multiplied or minus this value 513 divided again by this value, so you get the speed of 7 by multiplied by 10th power of 6 meter per second. So the galaxy is moving at this speed. Okay, they're asking the speed of the galaxy which is moving away from the Earth. So because it's moving away, it's a redshift, and that's why the wavelengths here is much bigger than the normal wavelengths. I think that's it for today, and see you in the next chapter.